Hey everyone, I just wanted to make you a video. Hopefully this is pretty quick to explain bias and variance, flexibility and inflexibility, and also overfitting and underfitting with predictive modeling. I'm working in R rather than Python right now. Please don't pay attention to any of the code. What you're going to pay attention to are the pictures that show up down in the bottom right area of my screen here. And we'll use those pictures to sort of drive our conversation. So what I'm going to do is I'm just going to have the computer choose some random data, um, and we're going to try to build a predictive model um, to model this data. So we're going to build some curves to model what's happening here. So I'm building a straight line model right now. That straight line model we can see fits the data pretty well. What we would say is this straight line model has high bias. It's not picking up any of the curvature that you might expect to see between the data points. It's really picking a very conservative model. It's biased against any like small intricacies we would see in the data. Let's see what happens when I take this x value here that's around 50, and I'm going to move its y coordinate. I'm going to take it away from like probably around 3,500 or so right now. And I'm going to drop it to -500. We're going to create a new linear model on this new data with this data point moved down. And I'm going to plot both linear models. So the existing linear model will show up in blue and the new one will show up in red. We'll see how the change in one data point did cause a change in that linear model, but it didn't cause a drastic change. So what we still observe is increased values of x are associated with higher values of y, higher output values. What we did see is the predictions on average have been pulled down by this observation, and the slope has changed slightly, but not by a lot. And so the model that we built, the straight line model with high bias, did change when one training observation changed, one of the observations used to build that model, but it didn't train drastically. Let's take a look now at what might happen if we train a model with high variance instead of high bias. So remember, variance and bias move in opposite directions of one another. If a model has high bias, it has low variance. Variance is essentially measuring how much the model would change if one training observation moved, which is kind of what we measured here, or at least what we're seeing here. So I'm going to build a new set of training data, new set of x values, a new set of y values. So here's the observations that we're going to use to train our model. Instead of building a straight line model now, though, we're going to build a curved model, and we're going to allow a lot of curvature. We're going to build a polynomial with degree 8. So this is allowing a lot of wiggling. We'll plot this model through the data, and we see the model fits the data really well. And we might be inclined to think, oh, this model is much better than the previous model. But again, let's see what happens if we take this training observation that's right around 50 and move it from just above 2,000 to now -500. So we're going to train this new model on the new data with that data point moved. And then we'll plot the new data with the blue model, which is the existing model, and then the new model resulting from the new training set, which remember has just got this one data point moved. That new model will show up in red. And so let's see what happens. Okay, and we can see a lot has changed. So here's the observation that was at 50 and just above 2,000. It was up here somewhere. Now it's moved down. And we can see that has caused a humongous change in the shape of our model. The red model is much different than the blue model. It hasn't even just changed locally, like near that training observation. This movement has caused drastic change very far away from that actual training observation. So this training observation has caused a giant variation in the model. And that's what the bias-variance trade-off is. So the more flexible we make a model, the more we're allowing that model to curve, the more susceptible that model is going to be to small changes in the training data. So a small change in the training data can lead to a really large change in the resulting model. Let's now move to the idea of overfitting versus underfitting. And so the idea of bias and variance has to do with how a model is trained and how the model might change if it's trained on different data. Overfitting versus underfitting is really concerned with how a model is going to perform on brand new data. How will the model do on data that it hasn't seen before? We'll run through a similar procedure where I'm going to build a training data set. So I'm going to build some X coordinates and some Y coordinates. Here they are. We're going to try to fit a model through this data. We're actually going to fit two models. We're going to fit a straight line model, which is a high bias model. It's not flexible. So this model will have low flexibility because it's not allowed to curve. Then we'll fit, again, an 8th degree polynomial model, which is allowed to curve a lot. It's allowed to be really wiggly. So we'll say this thing is very flexible. Now we'll plot both of those models on top of our training data to see how well they're performing. We can see the first model, the high bias, low variance, low flexibility model in blue, with the low bias, high variance, and high flexibility model in red. And we can see that the red model is doing a much better job fitting the training data. The blue model doesn't pass through many of the points, but it does capture the general trend. So you might be inclined to say that the red model is better, but be careful. The red model is better on the training data. It knew the answers in these cases. But how will the red model do if we generate some new data which follows the same distribution as the existing data points? So what we're going to do is we're going to generate 25 new data points. Those 25 new data points will follow the same distribution as the existing 10 that we trained the data on. What we'll do is we'll plot everything we have right now. So we'll plot the original 10 training data points. We'll plot the blue model, which was the high bias, low variance, low flexibility model, along with the red model, which was the low bias, high variance, high flexibility model. And now we're going to plot on top of that 25 new data points, which will act as brand new data that the models haven't seen before. Those new data points will show up in purple. Let's see which model does better. Does the red model still do better? Or does the blue model actually capture the general trend in a more reasonable manner than the red model does? And I think now we see, well, while the red model looked much better with the training data, it's not actually behaving very well with the new test data or this new simulated data. In fact, the blue model is doing a better job at capturing the general trend. And so what we would say is that the red model is overfitting. It's too flexible. It's too responsive to that training data, and it's fitting the noise. Noise is random fluctuation in the data that we can't explain. We never want to fit noise when we're building predictive models. So what we do want to do is we want to choose a model with the appropriate level of flexibility. That's easier said than done, but we'll identify some tools that help us choose flexibility later on in our course. As it stands now, though, we should understand that the red model is too flexible. It's too wiggly. It responded too much to the training data. And we're better off in this scenario with a more constrained, more conservative, and higher bias model, which is that blue model. The blue model does better at predicting new data. Let's look at one last scenario, which is underfitting, sort of the opposite of this idea of overfitting. Again, we're going to generate some new data. We'll generate 25 training observations this time. Here's the data that we're going to try to fit with predictive models. What we'll do is we'll build a very high bias model again. That's the straight line model. High bias means it's going to have low variance. It also has very low flexibility. It's not allowed to respond to individual training observations as well as a highly flexible model would be. We're going to build that straight line model. We'll also build a slightly less flexible model than we've been dealing with earlier. This is a degree 4 polynomial model. Basically, higher degrees can be associated with higher levels of flexibility, higher levels of variance, and lower levels of bias. So we're fitting a straight line model, and we're also fitting a 4th degree model, which has a higher level of flexibility than that straight line model does. Now what we'll do is same as last time. We're going to plot the data points, the training data. These are all these black points. We'll plot the high bias, low flexibility, low variance model in blue. And we'll also plot the high flexibility, high variance, and low bias model in red. And we'll see how the models do. And we see that the red model, the model with the higher flexibility, again does better in fitting the training data. And this will be true in general. Models with higher flexibility will typically fit training data better because they're allowed to respond more closely to the individual training observations. An inflexible model, a high bias model, can't respond to individual data points very well. And so it's not going to fit the training data as well as a highly flexible model will. But that doesn't mean that the inflexible high bias model is worse. Remember, we just saw that in the previous example, the high bias model with very little flexibility actually performed better on new data. We'll see if the same holds true here. We're going to generate some new data, 50 new observations now, following the same distribution as the original training data did. Those are those black points that we use to build our model. Again, what we're going to do is we're going to reproduce the existing plot with all of the training data in black, the low flexibility model in blue, the highly flexible model in red, and we're adding now these 50 new observations, and we're going to see, does the low bias model, the high variance, high flexible model, that's the model in red, still fit the data better when the data hasn't been seen by the model before? Or do we end up observing what we saw earlier and the low flexibility model, the high bias model, ends up fitting the new observations better? Let's see. We'll add in the new observations that follow the same distribution as the original training data did. These are all these purple observations here. And we can see now that the red model, the model with a higher level of flexibility, still fits this new data better than the straight line model did before. Basically, we chose an appropriate level of flexibility when choosing this red model. A 4th degree polynomial model here was the right choice. All right, so that's all I had for this video. I hope it makes this idea of the bias and variance trade-off a little bit more concrete for you. Remember, high bias models are these straight line models. They're biased against trends in the training data. High bias models have low flexibility. They're not allowed to curve very much. And they have low variance. They don't change drastically when new training data is used. We have the opposite scenario. We have high variance models. These are flexible models. They're allowed to curve quite a bit. They can respond very well to individual training observations, and they pick up trends in the training data really well too. The risk we run, though, when we use a highly flexible model with high variance is, well, there are 2 risks. The first risk is that if we had a slightly different training data set, we might end up with a very different model. We want to avoid that. So choosing the appropriate level of flexibility is really important. If a model's too flexible, it's going to change too much when different training data is used, and it's not going to perform very well when we try to apply it to new data where we don't necessarily know what the response is ahead of time. The other risk you run with using a highly variable model, a model with high variance, high flexibility, low bias, is that that model may end up overfitting, like we saw in this previous example, right? The red model was too responsive to the training observations, and it didn't fit the brand new purple observations as well as the high bias model did. All right, so again, that's a quick video on bias versus variance, flexibility versus inflexibility, and overfitting versus underfitting. One last thing to connect these terms together is that models with high bias have low flexibility, they have low variance, they're not likely to overfit data, but it is possible that they will underfit data. In the opposite scenario, we have models with low bias, have high flexibility, high variance, they're not likely to underfit data, but they are likely to overfit. And choosing a model that's sort of in between is going to be our task for the remainder of the semester. Again, I hope this helps. Thanks, everyone. See you soon.